Hi students, this video is going to be section 4.2, which is quadratic functions. We're going to do quadratic functions and their graphs, and then some max and min problems. So the most basic quadratic function is f of x equals x squared, right? You can plot a couple points of this function, and you will see that it looks like a parabola. That's because when the argument inside the squared is 0, it's going to reach its minimum point. And whether the x is negative or it's positive, it's going to be the same thing when it's squared. So it's symmetrical about that minimum point, which is the vertex. We can modify these in a couple ways. We can shift them up and down, or we can make them narrower or wider. So if we add or subtract a value after squaring the argument, that is going to give us a vertical shift, right? If we do something very last after squaring our argument, then that is going to just affect the output. Okay, so by adding 2, we shifted all the points up by 2. Now, if we want to shift horizontally, it's a little bit different. To shift horizontally, we are going to basically counteract what is happening to our x. So in this example, by adding 1 to the x, what happens is, remember in our original equation, our minimum point happened when the thing being squared was 0. Okay. By adding 1 to our x, in order for this thing being squared to reach its minimum value, x is going to have to be -1. So our vertex is going to shift to the left by adding 1. Okay. So to shift left and right, you are going to subtract however much you want to shift to the right. Okay. And that's going to be from the x value directly before squaring it. You can go ahead and plug in a couple values here, and you'll see how x has to be shifted to the left one in order for this function in blue to behave like this function in red. Then third, we can also change how rapidly our parabola opens up and or flip it upside down. So here we're going to put a coefficient of -3 on our variable term, and the negative is going to flip it upside down, and the 3 is going to make it grow 3 times more rapidly. So it basically stretches it by 3. Okay. You might want to pause the video here and plug in some values of x and plot some points in these 3 or 4 different scenarios to make sure you understand how and why our quadratic functions are behaving this way based on where we are modifying the function. Okay, so just to recap, if after we've done everything to our x variable, we add or subtract something, that's going to directly affect our y coordinate. So by adding 2, we shift up by 2. Very straightforward, shifting in the y direction. The x direction is just a little bit trickier. We're going to shift kind of the opposite of how you would think, and then we have to add or subtract directly to our x itself before squaring it. We'll shift us sideways, and it's going to kind of shift us backwards from how we think we're going to act, because we have to remember, for our function to behave the same, it's going to have a vertex where this thing being squared is 0. So that vertex is going to shift to the left one because this is 0 now when x is -1. And then if we want to make it open up more or increase more rapidly, we will multiply it by a number bigger than 1. And if we want to flip it, we'll multiply it by a negative sign. Okay, so we can put all 3 of these pieces together. Here I have you can just see our f of x equals x squared, what it looks like. If we add a 1 to the x, it's going to move to the left 1. If we add a 2 at the end, it's going to move us up 2. And if we multiply by -3, it's going to flip us upside down and make us move 3 times steeper in the y direction. Okay. So these are the 3 pieces. These are the 3 pieces of manipulations that we can perform. And we represent them by 3 different letters just so we can talk about them representationally. So in this case, this -3 is what we're going to call our A. A determines which direction we open up and our steepness. This is actually a -1 because we like to say that we are subtracting something from x to shift in the x direction by -1. And then, and that's called our H. And then this last one is called our K, and that is how much we are shifting in the y direction. So let me describe this, this plus sign and why I'm calling it a -1 here in our general form will start to make more sense. So the general form of our quadratic equation, our function is going to equal a times x minus h squared plus k. Now here, h and k are where our vertex are. So remember, our vertex is at -1, +2. So that's why we like to think about what are we subtracting from x, because that's going to be the x coordinate of our vertex. So yeah, if we have the A is how much we narrow by, the H is how much we shift right, the K is how much we shift up, and our vertex is at that HK. Do play around with this, plug some points in to make sure you understand how tweaking each point changes the way your function behaves. I am not going to need to do these examples in this function, in this video. If needed, I can make another video to do these examples for you guys. Let's talk about one more piece of our quadratic equations, or quadratic functions, and that is working in our standard form and also determining our intercepts. So for this function here, f of x equals x squared minus 2x minus 3. Notice it is not in the same form as we are used to, all right? So we can't see what our h and k are here. To do this, we have to complete the square. So we can complete the square just like we did to solve quadratic equations. And remember, that is where you identify the coefficient on your x term to engineer a constant term that makes this factor as a perfect square. So since the coefficient on our x term is a -2, we're going to take -2, divide it by 2 and square it, and that's going to give us a 1. So we need a constant term of a 1 to factor this into a perfect square. So to get that constant term of a 1, we're just going to add 0, which is +1 minus 1, and then kind of ignore those pieces, that -1 and that -3 that we don't really need. Okay. Now our first 3 terms are actually a perfect square, so we can factor them as a perfect square. So now, just by adding 0, we have factored our quadratic into a perfect square, and now it's in that standard form we're used to, where we can graph it. So we can see that our vertex is going to be x is +1, y is -4, and that our a is 1. And the a being 1 means that when we go 1 to the right or 1 to the left, we're going to go up 1. So the a being 1 really means your first move away from the vertex is going to be up 1 over 1. Now that's going to change as you go farther up. Okay. So if we are in this other form, you have to complete the square before you can graph it. But now we might also want to find our x and y intercepts. Usually we actually just care about our x-intercepts because that is where our output is equal to 0. But let's take a look. If we want to find our x-intercepts, that's just when our y equals 0. So we set y equal to 0, we solve our equation. And in this case, we don't have to use completing the square to factor. We could if we wanted to, but it is just fine to factor it this way. And we get that our x can be 3 or it can be -1 when y is 0. And so our x-intercepts are going to be at -1, 0 and 3, 0. If we wanted to find our y-intercept, we could do the same thing, just set x equal to 0, and we would see that our y-intercept is -3. So usually if we are in our standard form, which isn't easy to graph from, we would complete the square to see our vertex. But we can also take a shortcut to calculate what the vertex is when we are in standard form. Here in our standard form, we're going to call our coefficients A, B, and C. These are different than our A, H, and K, although the A's are the same. Notice how we call it A, H, and K when we are in this square completed form. And you can identify when we are in this general form where the square has been completed because we only have one x. Because it has been factored into a perfect square, you only see the x appear once. Whereas here it is in the unfactored form. And so you see the x squared term and an x term. Okay. So from that standard form, we can calculate the vertex just using these 3 coefficients. All right. And it actually comes from completing the square on these leading coefficients. So here I'm going to complete the square on this generalized standard form. And when I am done with that, I see that our vertex, our x coordinate of our vertex is -b over 2a. So if you want, you can always find the x coordinate of your vertex by just saying -b over 2 times a. Okay. The x coordinate of a vertex is -b over 2 times a. Technically, our y coordinate is all this stuff here, but a lot of times instead of plugging in the b, a, and c and all this stuff here, it's actually easier to just figure out your x coordinate, -b over 2a, and then plug that into your function. And that will be where your vertex is if you want to calculate the vertex without completing the square to graph. Let's do a little bit of min-max problems. We have one example from the textbook. Remember, the minimum or the maximum of your parabola is going to be at the vertex. Your vertex is going to be the minimum if your parabola opens upwards, meaning your a, your coefficient on your x squared term, is positive. And your vertex is going to be a maximum if your parabola opens downwards, meaning the a is a negative. So these are great when we have scenarios. When modeled, they are quadratic equations or quadratic functions because we can either find the min or find the max to know kind of an ideal situation for ourselves. So in this case, a farmer plans to use 100 feet of fencing material to make a garden plot that he wants to make as a rectangle. Okay, no funny shapes. Along the side of a barn. He's going to use the barn as one side of the plot. How should he split up the fencing among the other 3 sides in order to maximize the area of the garden plot? All right, so we are going to let x represent the length of one side of the plot. And then the dimensions of the plot are going to be x feet by 100 minus 2x feet. All right, does that make sense? Because we only have 100 feet of fencing. So if one side is x, then the other 2 sides are going to be whatever is left. Or sorry, if the 2 sides that are the same are going to be x, then the other side is going to be just whatever's left after we do those 2 sides. Okay, whatever's left from our 100 feet after we make the 2 sides that are represented by x. If that's the case, that one side is x and or sorry, two sides are X and the other side is 100 minus 2X, which is what's left of our fencing, then really the side against the barn is also 100 minus 2X. So our area is going to be X times 100 minus 2X. So what we want to do is maximize the area of the garden plot. So here's a diagram that might help it make more sense. He's making a rectangle. He's going to fence these three sides because the other side is going to be, we're going to use the barn to fence the other side. So he only needs, so this perimeter for these three sides is going to be 100. If we call this side X, then this side is also X. So the remaining fencing is going to be 100 minus 2X. Okay, so that's how we decided the length of these three sides, and they can change depending on what we decide X is. We can make X really big, and then would be small, and then what's left over here is going to be small. We could make X really small. We're going to assume that the barn is big enough. We can, let's just say the barn is really, really long. We don't have to worry about it running out of a barn for this other side. And remember, the goal here is to maximize this area. Okay, so now that we've set our X, we know the formula for the area is just length times width right here. So we multiply our length times our width, and we get this formula for the area. We can see, because our A is -2, that it's a parabola opening down. So the vertex is going to be the maximum. All right. Using the formula, the vertex for vertex that we just calculated, we can see that our vertex is at X equals 25, and our area for our maximum area is just going to be our function evaluated at 25. So if we want to maximize the area, we're going to let the two sides attached to the barn be 25 feet, and the other side is going to be 50 feet. The resulting maximum possible area is going to be 1,250 square feet, which also happens to be the value of our area function evaluated at 25. Okay. You might want to take some time looking in the textbook at these problems, because once you get the hang of them, they're actually really fun.